right. We're live. That's quite incredible. Okay. I think we all moved. But yeah, there was a little bit of trouble. So, Thurston started. So I will just say that we're starting our Raffael sequence, and Raffael Stenzel is our first speaker in this sequence. And the topic is Infinity One comprehension schemes.
Yeah, hi, thanks for having me. It's a great pleasure, and thanks for joining me in the Buenos Aires cyberspace. Now, let me start with making a few comments on the context. So the term comprehension is used rather generously and ubiquitously in categorical logic. And I want to specify that the notion of comprehension that will be subject to this talk today is based on a paper of Benabou in the early 70s and was then later developed by Johnston. I am not aware of any developments in the meantime. Maybe some of you know as a reference that would be actually interesting. So the notion I will introduce today is a generalization of what Johnston did in The Elephant. So I personally stumbled upon that concept when I was browsing his book for a framework to capture certain characteristics of univalence, which I will come to talk to in the end of the talk. And then generally developing this concept infinity categorically, it quickly turned out that certain one-categorical shortcomings are beautifully resolved in the infinity categorical world. And it captures even various intrinsically infinity categorical notions. So this is a natural environment for this notion to live in. Let me just figure this out. Great. So just a quick overview. I will start with a little introduction that ties the rather technical definition I will give later to the original set theoretical notion. Then I will give the fundamental basic definitions and a few examples. So if we think of comprehension schemes as theories, although this will be syntax-free, but let's think it might be beneficial to think of them as theories and certain fiber categories, certain fiber infinity categories as structures that may or may not be models of those theories. And then we will just have a look at certain examples to see what kind of stuff these theories, these comprehension schemes can express. What I want to get to are the applications. So first of all, we will give a characterization of those external Infinity One categories, which are represented by an internal counterpart in terms of comprehension schemes, and then apply this to the notion of univalence in the infinity categorical world. And in the end, if there's time, if I did not miserably miscalculate the schedule, I will say a few words on the meaning of those notions in the world of model categories. All right, so yeah, fasten your seatbelts. To motivate, originally, this notion is based on the axiom scheme of heuristic comprehension, sometimes known as separation or specification. And it was one of the first axioms, or maybe if not the first axiom of what is nowadays known as ZFC. So we remember that that axiom scheme states that for every set X and every class S that is represented by a first order formula in the language of set theory, which may have additional parameters which are suppressed here. If we are given those two things, then the intersection, which is a class by definition, will be again a set. Now, it is often read in the way that thinking of sets as small classes, right? It's a size, it's a notion of size. And Benabou gave an intuition to think of the elementary embedding of sets into classes as a sort of Yoneda embedding, where we think of classes of properties over set, and where we think of the small sets as the representables. Then what does comprehension say in this interpretation? It says this: if we're given a representable X and some general preshift S, then a certain pullback of X and S is again representable. So let's keep this in mind. I want to now give a first look. I want to have a first look on this infinity categorical notion. So we would think of the meta-mathematics that we're doing is, in the first case, naive set theory, right? And on the other hand, we will just do the usual infinity category theory, which is enriched over the infinity topos of spaces. Now, to understand what comprehension schemes mean in this context, let's compare the other notions. So we start with a set theoretic universe V, right, which is a model of a certain fragment of naive set theory that we want to formalize. And the counterpart will be not just an infinity category, but an index infinity category. So it's more flexible in general. Then we were given a set X in V, which is an object. And rather than just looking at objects, we will consider arbitrarily shaped diagrams in that index category. A class S is then an external structure which does not live in our set theoretic universe. And rather than looking at formulas in some language that might not be given, we look at extensions of shapes. So if we start with I shapes, then we can look at extensions of I shapes to J shapes, where J is another infinity category. Then we looked at the intersection of S and X, which we think here as X extended by the condition that S holds. Let's think of this property as structure, somehow trivial structure. Then on the other hand, we will have an actual presheaf over C, which is the category of J-shaped diagrams which extend I in a very well-behaved way in this world of indexed infinity categories. And then what does comprehension mean? Well, we had that comprehension for the set theoretic universe holds applied to one specific class S if this intersection is small for every small set. On the other hand, we will consider this presheaf of J extensions of this given X, and we want that all these presheafs are representable over C. All right, I will get to this definition on in 2 slides or 3 slides. Let's just keep the lower right corner in mind for intuitive purposes. Now, to just throw a few notions at you that will be used extensively in the following. So, given an infinity category C, we can look at index infinity categories over C, which is just the category of functors, the infinity category of functors, typed accordingly. And likewise, we can look at the infinity category of C indexed groupoids, which is just those index category which happen to land in infinity groupoids. Now, this happens to be the infinity category of presheafs over C, right? Because our base notion is the notion of infinity groupoids. This is somehow a tautology in infinity category theory, but it's an intrinsically infinity categorical tautology, which is very important for certain notions to work out very well. So for the rest of the section, we will just fix a given C and period. Furthermore, there is a way to move from indexed infinity categories over a given C to fibrations, to fibered categories over C, and vice versa. This was dubbed the straightening unstraightening construction, which is an infinity categorical version of the Grothendieck construction. Indeed, we have seen in Peter's talk earlier today an instance of that, right, where we moved in between categories of attributes and discrete comprehension categories. That was a special case of the one categorical Grothendieck construction. We can restrict on both sides to, on the one hand, to the indexed infinity groupoids, and if we unstraighten those guys, we obtain right fibrations, which are the infinity categorical version of the discrete fibrations. All right, so we will sometimes freely move from the left to the right and from the right to the left, depending on where the things are easier to define. The last preliminary definition is the definition of a core. So if we start with an infinity category, then we can assign to it the largest infinity groupoid contained in it by just throwing away everything that is not invertible. And if we can do this for one particular C, this is a functorial assignment, we can do this for index infinity categories as well, namely by starting with the Cartesian fibration, straightening it, and then taking the core, and then we obtain a presheaf by composition, and then we can unstraighten it back. And what we obtain is a right fibration, which I will call the core of P and denote by P cross. So we, an analogy to throwing away the non-invertible arrows, P cross can be obtained from P by throwing away all the non-Cartesian arrows. All right, so what is this context? So if we are giving an indexed infinity category and it's unstraightening P, so they correspond to each other, then let's start, let's assume we are given a simplicial set I, or more specifically infinity category I, it doesn't matter here. Then we compose as given here. So we first consider the values at I, then we exponentiate with the simplicial set I, and then we take the core. By unstraightening, we obtain a presheaf sorry, this is a pre-sheaf. In the unstraighting, we obtain the right vibration over C, which we call the p-rectangular diagrams of shape I and E. It's quite a mouthful. So what we can think of is, as a fibration, it consists of the fiber-wise I-shaped diagrams, and the natural transformations are not fiber-wise, but they're perpendicular to that. So the natural given a fiber-wise diagram over C and another fiber-wise diagram over D, then a natural transformation consists entirely component-wise of Cartesian arrows over the same arrow over C. So they are kind of prismatic in a way. And we recover our notion of a core if we take the simplest diagram there is, or well, the second simplest after the empty one. So if you just look at the rectangular points, then the middle arrow is the identity, and we recover the core. Now, there is a rather opaque definition following from that, which is the generalization of Johnson's notion. Namely, if we are given a functor from I to j, then we say that a fibration satisfies G comprehension if the restriction has a right adjoint, which we will think of indeed as an extension of these things. Now, that doesn't look like it means anything, but to come back to the table we had at the beginning, let's just look at what this means. So if we start with our fibration P, and we are given the functor G and a specific fixed rectangular diagram X, then what does it mean that the bottom arrow here, the restriction, has the right adjoint? Well, you can check this by checking if they're universal arrows, meaning co-units in this case. And so it means that this pullback here, the over category, has a terminal object. Now, this top arrow here can be post-composed with P to land in a slice over C. And that this guy here is a terminal object basically just means that for every diagram X, this map here is up to categorical equivalence representable, a representable pre-sheaf. In fact, if G is a monomorphism, it is a pre-sheaf already, and then it's a strict, like a straightforward representability condition. All right, so this is still not very explanatory, so let's look at examples, right? And I want to look at exactly 3 examples of such schemes. So the first of all is the comprehension scheme called smallness. And we say that P is small if it has comprehension with respect to, well, this trivial map here. Now, if you check what it means, it just means that E cross is a terminal object. In other words, that it's representable over C. This is a perfectly fine condition. It looks very innocent, but it's actually one categorically very poorly behaved. And it is the reason why, well, for instance, it's not even stable under equivalence. Many examples you would like to be small are not small. And it is the reason why Johnston in the book then moves away from that notion and defines it entirely differently. And it will turn out that in infinity categorically, it's a perfectly good notion. We say P is locally small if it has comprehension with respect to the one boundary inclusion, whatever. And furthermore, the last example I want to consider is well-poweredness. P is called well-powered if it has D0 comprehension, but not entirely, but a generalized version of that, namely restricted to monomorphic diagrams. In this case, this means that if we look at the restriction between the rectangular diagrams, then we can look at the restriction of this guy to those rectangular diagrams where every edge is not just an arbitrary edge, like an arbitrary vertical edge in E, but a monomorphic one. And that defines what is called the generalized comprehension scheme. So let's look at the instantiations in different fiber categories to see what sort of stuff they can express. Yes. So, for example, if we start with the representable right fibration, which is the fibered version of the representable pre-sheaf, then it's by definition small, right? That's how we define smallness. It is locally small when you can compute the restriction here, which boils down to just being the diagonal of this form, has a right adjoint, which again just means that C has equalizers with codomain C. So all representable fibrations over C are locally small if and only if it has all equalizers. So comprehension schemes in certain cases can express the existence of certain limits. Another example. Let's assume C might not be a small infinity category theory, but potentially large, cardinality-wise. Then C is small, or respectively locally small, cardinality-wise, if and only if an associated fibration, which is basically a directed infinity categorical version of the fibration of families that you might know from ordinary category theory, if and only if this guy is small, respectively locally small, in the sense of these comprehension schemes. So they can express cardinality issues. A third example is, well, given C, it's always fibered over the point, right? Because it's an infinity category. Now, in this fibration, the Cartesian edges are exactly the equivalences in C. And if we look at what the rectangular diagrams there are, then they are exactly the functors from I to C, and then we take the core of the whole thing. So if I happens to be an infinity category, then this is exactly the infinity category of functors from I to C. Then again, one computes that this guy is small if and only if the core of C is contractible, and it is locally small if and only all Hom spaces of C are contractible. So in some sense, the base structure, which is contractible, can we tell only about contractibility. All right, a very important example is if C has pullbacks, then we can fiber C over itself in a canonical way by looking at the target fibration. This is also a theorem or proposition that is true once categorically, namely this guy is locally small, if and only if C is locally Cartesian closed. All right, so we have seen lots of examples of small and locally small fibrations. And you can use those examples to show that smallness and local smallness are generally mutually independent. And in fact, they are not only mutually independent, but you can show that in conjunction, they are generic in the following sense. Namely, a Cartesian fibration satisfies both these comprehension schemes, if and only if they have J comprehension for every finite monomorphism. So every monomorphism between finite simplicial sets. The way you can prove this is, well, given such a Cartesian fibration, you'd look at the class of all arrows G between simplicial sets, such that the fibration has comprehension for those guys. And then you show that this has very, very nice closure properties. And then you can do an induction along the skeleton decomposition of finite simplicial sets. All right. Now let's go to the applications. First of all, let's start with internal infinity category. So I will not give the definition. I will not have the time for that. But you may know the definition of an ordinary internal category in one category with pullbacks, which is a reflexive graph, which is a monoid and some monoidal structure over the product C0 times C0. And there's a process of externalization of internal structure. The way I think of it is sort of a directed Yoneda embedding. So you take an object C, and instead of just looking at the representable into C0, which would give you a set, you get a category by looking into arrows into C0, and which gives you the objects, and the arrows are the lifts of two such things into C1. Now, analogously, if you know what an internal infinity category is, whatever it is, if C has pullbacks, we can do an analogous construction here. And what we obtain is a functor, the externalization functor, which starts from internal infinity categories, which are complete Siegel objects in C. This is the way they are defined usually, and spits out an indexed infinity category of C. Now, the reason why you can think in this case especially of the externalization as a direct Yoneda embedding is if you're restricting both sets to infinity groupoids, then you start with an internal infinity groupoid, which is basically just an object in C, and you get out an indexed infinity groupoid, which is just a presheaf over C. And in this case, the externalization exactly spits out the representable of C. We know that, for instance, if C was a presentable infinity category, then we knew certain criteria to check whether a given presheaf is representable or not. So in this directed setting, we would like to know, well, given an index infinity category theory, how can I find the internal presentation of that guy? And here we have a very nice characterization, namely, if C has pullbacks and we are given some Cartesian fibration or an index category over C, then this guy is both small and locally small, if and only if it has such an internal representation. So this restricts, in the case of presheafs, to the fact that P is small, which is just another way to say it's representable, if and only if there's an internal infinity groupoid. So this is not much of a statement, but the first one is where the juice is. So this is very nice. Why is this nice? So, for example, a very prominent example of this guy is the universal Cartesian fibration. There is a universal Cartesian fibration such that every other small enough small here cardinality size-wise. Cartesian fibration arrays this pullback of this guy. And one can show that this is the externalization of some internal category. In fact, the 3D I don't know how to call this guy, but I call it the 3D walking internal infinity category. This is very helpful because, for example, there are general transfer results of comprehension schemes between different, if you have functors between fiber categories, then there are certain transfer results for those. And for example, you can embed infinity groupoids in infinity categories. This guy has left the joint by just assigning the free infinity groupoid of infinity category. And using that, you immediately recover the result that is in Lurie's book on higher topos theory, that the universal right fibration is representable as a pre-sheaf by the terminal object. And there are other examples I will not get into. Okay. Now there's another characterization, namely if we are not given if we are given an indexed category which we don't really know how to unstraighten. Maybe that's complicated. Maybe we're bad at math. I don't know. We might want to ask for a direct criterion to see if this guy has an internal presentation. And at least if C is complete, which is of course much stronger than just having pullbacks, right? But if C is complete, then an indexed infinity category has a presentation if and only if it has a left adjoint. So this is a criterion which sounds very different. But as a corollary, I don't know how useful it is, but it sounds kind of cool, that if C is complete and we are given an index category I, then it is internally represented if and only if it satisfies all comprehension schemes that are satisfied by the universal Cartesian fibration. So in some sense, again, the universal Cartesian fibration is in some sort of generic also in this sense. All right, so we had the HoTT workshop, so let me say a few words on univalence. So first of all, if C has pullbacks, again, we can fiber it over itself by the target fibration. And then it's easy to define what the full comprehension affinity category of C is. Namely, it's the full subfibration of this guy. Intuitive generalization of the definition we have seen in Peter's talk earlier. An example, or the only important example for this talk of this guy is if we are given a map Q and C, then we can look at the family of all maps which arise as pullback of Q. And this will give us an example of a full comprehension category. Then we have the following proposition. If C is locally Cartesian closed, so we can define univalence in the first place, then we obtain another representability result in some sense. Namely, if we are not given some indexed infinity category, but full and complete comprehension category J, then it is small if and only if there's not some internal presentation, but actually a univalent map in Q, which represents this guy. So we can characterize univalence by smallness in the context of comprehension categories. Now, in fact, one can show that a given Q is univalent in C if and only if it's terminal in the core of this guy, which is equivalent to say that it's one truncated in the bigger core of the whole target fibration. Now, I don't know how useful it is either, but this suggests a general definition of univalent objects in arbitrary fiber infinity categories, right? We could just take any E to C and say that an object in E is univalent if it's -1 truncated in its core. Okay, so yeah, I will just quickly gloss over that. Namely, there is a proposition by Gebner and Koch. When C is presentable, then they show that univalence in some sense can be expressed as a sheaf condition of this functor, right? They show that Q or a map related to Q is univalent if and only if this guy preserves limits. This can be generalized away from the presentability case if we still are happy to assume completeness, locally Cartesian closeness. Then Q has a univalent retract. Let's forget the retract part. If and only if its associated family of pullbacks is a left adjoint. Cool. So this suggests some nice definitions in the context of infinity toposes. So there is a definition of elementary infinity topos suggested by Schulman and then picked up by Masaryk and a few papers.
Does it say 20 out of 26?
Oh, excuse me, sorry?
So I don't know what suggests what exactly, but I suggest that we wrap up really soon. Just in case.
I still have 2 minutes, 3 minutes. That's fine.
Okay, 2 minutes is fine. Okay, great.
Yeah. Sorry. We can capture being in elementary high topos by comprehension schemes by defining C to be well-powered. Sorry, not C itself. The target vibration to be well-powered, and that it is covered by small neighborhoods in some sense. So we can characterize elementary high toposes as well-powered infinity categories which have a cover of small neighborhoods. Yeah, we can do a similar characterization of Grothendieck infinity toposes, where we have a notion of cardinality, and it turns out that a presentable C is an infinity topos if and only if this guy here is locally small, and we have an infinite amount of comprehension infinity categories which ought to be small, or by alternatively, we can rephrase condition 2 to just ask to talk about one single vibration instead of infinitely many, but ask infinitely many comprehension schemes instead, which might be dubbed kappa superpoweredness, whatever. Okay, there are, I have maybe just 1 minute of model categories. So in the context of model categories, it might be surprising, at least was a bit surprising to me, that this notion still has meaning. Let me just gloss over this. So you can define an externalization functor in this world, and it turns out that the externalized complete Siegel spaces correspond exactly to the right equivalent functors into the Joyal model structure, and the complete Siegel groupoids in some sense correspond to the right equivalent functors into the Kahn model structure. So smallness and locally smallness in conjunction become right equivalent conditions. And one can take this further. Sorry, I'll skip this. And see that this right equivalent condition is in some sense two-dimensional. And if we look at this family of pullbacks of a given map, then this two-dimensional case actually recovers what is known as the weak equivalence extension property, the vibration extension property, which become two-dimensional right equivalent conditions. And then there's a comparison between those two, and this comparison actually gives you the equivalence of those concepts given the necessary assumptions. And yeah, that's it. Sorry, I made it.
You kind of made it, yes. Thanks a lot. So I'll let everyone applaud in their way of choice. And if there's like extremely short question, not a whole speech, I would allow it. But yeah, if not, we have just a couple of minutes or a minute to move to the next room. So is there a quick question? The next talk steps in 2 minutes. So
yeah, sorry, this was super fast, I suppose. Yeah.
That was a bit, I mean, it was great. Just
of course. Appreciate
I've had like 5 questions.
compliment.
I've had 5 questions along the way, but I'm gonna, I was gonna ask in the interest of time. Okay, folks, that is it for this session. So we're gonna be in 1 minute in the next room, and we're gonna continue with the Raffael sequence. So we'll see you there. All right.